Hello?
Hey,
Hey,
Harry.
Wilson. Sorry I'm late.
Hey, that's okay.
All right, then. Let's go ahead and get started so I don't take up too much of your time here. I'm just going to take a look at the notes. We have a data structures algorithms interview today.
Yep.
Okay, cool. Do you have any interviews lined up for in the near future?
No, unfortunately, I think.
Okay, that's fine. Let's see here. So I'm just do you have a specific level in mind for your planned interviews?
So I am applying for a senior
Okay.
software engineer position. So I want to simulate like what a real interview is going to ask. Yeah.
Okay.
I think we had more interview before with you. So this is my second time.
Okay. And cool. So we're doing Python. I'm gonna check to see if the compiler is running. Perfect. And now spend a little bit of time talking about the problem. Feel free to pause me whenever you have any questions.
Okay.
Let's see here. So I have a tree, and the tree has, one root and children per tree. So here we can have three children. Sometimes we can have one child. Sometimes we can have two child per tree per node. So it's an n-ary tree,
Okay.
and I have a grasshopper that starts at the root and picks a random child and then traverses until there are no more children. So for example, if we start the root that's right here, the tree is sideways, by the way. So we started the root that's right here, then we go here by random. We can either go here, here, or here. So we'll just go here on random. Then from here we have two, so we'll just go here on random. That would be the way we traverse. So let's say we do this infinity times. We want to find the probability distribution of grasshoppers ending their traversal at each node. So here we have 0 at the root because there are three children at the root, which means that the grasshopper will never stay here because we keep traversing until there's no more children. So it's just still children. Probability of a grasshopper being at this node is 0. From here, right, there's a 1/3 chance of the grasshopper landing in this node. That's why we have 1/3. And also the same here. So here we have 1/3 to this node, and then this node has exactly one child, so it would be here for 1/3. But this one would be 0 because there's a child. Same would go here, right? Here is 1/3, but since there are two children beyond that, it would be 1/2 of 1/3, which would be 1/6 and 1/6.
Oh, I see. Oh, I see. Okay. That seems to make sense. So I think like when we start with root, depending on how many children there is. So in this case, from the root, there are three child. So that means when I go to each child, I can the probability for the child, let's say the upper child, when I go to the upper one, it will be the probability will be 1/3 that I can pass it down to this child because they have three children. So, and then when I pass it down 1/3 to these children, then The children will get the 1/3, and that is the base probability. And then depending on how many children there are also underneath, if there is no children, then that is a probability. If there is, let's say there is another two child underneath this, then I will just keep dividing that probability 1/3 into half, and then distribute evenly to is children. If there are children, let's say there are 2 children, right? And then until you just keep dividing depending on the number of children there is until you hit the root, until you hit the no more children, which is at the lead, and that whatever the value or probability that got passed down, that is the final probability. And same thing for this child. This is one past 1/3 here. And since there are 2 child, then you divide 1/3 into 2 based on the number of children. And then this node now is the lead node. So that means 1/6 is the probability for this, and same as this. And this one is 1/3. Also, I'll pass it down here, and saying there's only there's 1 children, then you just pass the whole thing. And then 1/3, and then at the end, this is no 1/3. So I think this is kind of the strategy. What do you think?
Okay, that sounds good. What's the time complexity of this?
Time complexity, so probably since this is an n-ary tree, so there may be n children, and then we need to traverse all the nodes until the end. So that means it will be like this is like n-ary tree, so it will be n to the power n. When depending on what the n is, that's the time complexity.
Okay, sounds good.
Then do you want me to start writing code?
Whenever you're ready. Is there
okay.
something that you want to get more clarification on?
Oh, and how do we return the output? Or
It's a good question. So basically, we want a way for us to store this probability. So you'll see that for each node, there's a number. But beyond that, there's no other identifier. One way that we can do this is by having this class. So probability would be this. Children would be a list of other known objects like that. It doesn't have to be a list. It could be any sort of data structure you want. But that's one way we can do it.
I see.
Anything else you want to take a look at?
So that means we will be given a tree that the probability is just all zeros, and I need to update all the nodes.
You can assume that the probability value is equal to 1 for the root, and then it is 0 for all the other nodes.
Oh,
so
I see.
At the very beginning, this tree will be 1, and then everything else is 0.
0, okay.
Like this.
I see.
Then after we run, I don't know, assign
Okay.
probability on the root, it's going to look like that.
I see. Okay. Okay. I think that yeah, that should be enough information. So okay, I can start on that. So root, um, and then okay, start with so the root. Okay, what? Okay, I think I can assume. Okay, maybe I can just make sure. Just handle some edge case if root. Just I think I just maybe returned. Then so that will be I actually if or root actually this is not return. And then if root children equals to 0, that means there's no children. So that means that's the probability. The one that is set at the root, that's the probability. So otherwise, though there are children, then I could do the I want to use a helper so that I can traverse the tree in a recursive manner. So this will be and actually I need to update the root probability 0 and then pass in root and also the probability. So this should start with the 1 to begin with. And then I will have helper root, and this will be the probability. So this so if we those so that would be a base case, right? Base case, which is if root children is 0, that means there's no children. and which means I can assign whatever the probability is being calculated and passed on to the trial. So probability. So then else because this is so which means good. So if they're children, then the root and the note that I'm doing, otherwise just use note maybe this thing more clear. This note. So there's children, so that means I assign myself to 0. And then I can traverse each children, but depending on the number of probability, I need to calculate a new probability for each children. So you equals to probability divided by just the length, and then can say for range 0 this is range. So we iterate for each children, and then I can say note children new probability. So that will traverse to each on each trial. And if it is a deep node, then whatever is being probability is being passed down, that will get assigned to the node. Oh, and then this was a return. So if not, then continue to pass the probability, the new probability to each children. But as a parent, I need to set myself to 0 since I have a children. So let's see. So again, I think maybe I can do some dry one and testing and make sure that it is the code is good. So let's say I use this example. So root is it is false and children is 0, which is not true. So go down here. So I assign the probability. The root is 0, and then I call my helper function, pass in the 1 to the as a probability to begin with. Then depend on let's see here. If no children is 0, which is not true at the beginning, then I will go to here. So probability is 0. Actually, this is not needed because I have assigned some in the helper function. So I can just say this pass the root probability, which is 1 to begin with, but then in the helper function, this will get updated to the correct value is 0, and then divide the probability based on the number of children, and then pass it down in the helper function to each student. So, and then each student will just let's say if this is the first student, I'm invoking the helper function for that student, and this will become the 1/3. Then the name of the children is which is false, so this won't get executed. And then I need to assign probability to 0, and then depending on that's only 1 children, so probability is still 1/3. And then this will call the 1 children here with 1/3 probability. Then here, now I'm reaching the leaf node. There's no children, so the probability I think assigned to this node is 1/3, and then return, and then go back up, and then go to the next children.
Okay. Cool. So in this case, what would be your time complexity?
Time complexity, so it's still depending on the number of children, because I'm traversing. I need to traverse all the nodes. So depend if there's n. It is the end of each tree. The worst case, you could have like n number of children for each node. So it could be n.
Okay.
So it could be n squared.
Okay.
Oh, n to the power of n. Sorry.
N to the power of n.
Yeah, because
let's say you have n was the total number of nodes. So
n was the total number. Okay. Oh, okay. Sorry. N as a total number of nodes. Okay, I see. Okay, I thought n is the number of children. Okay, sorry.
We just reuse n. It doesn't have to be the same variable. So in this case, n is the total number of nodes. What would be your time complexity?
Oh, okay. Then it will be just n. You need to traverse all the nodes.
Okay. Okay. Good. What about space?
The space, well, other than the cost that there's no other auxiliary space, there's no output, there's no space needed for output because we are just updating the same tree as an input.
Okay.
So it will be just the whatever the height of the tree, that will be the maximum cos that, number of cos that.
Okay.
Yeah.
Good. So we'll just keep on building this problem. We still have one more problem to go through here, or
Sure.
multiple as many problems as we need be. Have you heard of and I'm just going to type below line 66 here.
Okay.
Second problem. Have you heard of a DAG?
No.
Have you heard of a DAG?
Oh, sorry. Oh, that. Okay, sorry. Directed ASIC graph. Yeah.
Directly acyclic graph.
Mm-hmm.
So same as before, the edges will be one way. Acyclic meaning that we won't have edges that go back towards the same previously seen before node. We can also assume yeah, that's all we can assume, that we have no cycles and that all edges are direct.
Okay.
So same as before, we still have a grasshopper that starts at a root,
Okay.
or in this case, it would be a root like this,
Okay.
and traverses outgoing edges until there are no more outgoing edges in the
Okay.
outgoing edges at random,
Okay.
traverses from one node to the other node until there are no
Okay.
more outgoing edges in the node.
Okay.
We still want to find the probability distribution of grasshoppers ending their traversal at each node. So it's going to be a lot more clear if we have an example here. So same as before, left to right, we have this. So we can check to see what the root is by which one has no outgoing edges. And then let's say it's here. We pick outgoing edges at random. So here to here or here to here. That's the possible areas we can go from here. So this would be 1/2. This would be 1/2.
Okay.
Okay. And then from here, 1/2, we can go from here, 1/4, or here, 1/4.
Oh, okay.
And then from here, we can go here, 1/4, or here, 1/4. Except this one already has a 1/4. So it's 1/4 plus 1/4, which equals 1/2. Because this one already has a 1/4 probability from here going to here.
Okay, I see.
So when this one goes and splits again here, it would be adding it.
Oh, I see.
Okay. And another thing that we need to clarify here is that we cannot use the tree.
Oh,
So we need to figure out a different way. So for us to
okay.
traverse the DAG.
So, okay, so this is not the data structure available. This is not available anymore.
No, it's not relevant anymore.
Okay, I see. So we need so does that mean the oh, so what is the representation? What is the data structure for this DAG? Is it
Do you have anything? Do you have any preference?
I think we could use maybe adjacency list.
Okay.
That's one. I know there's some other efficiency matrix on it, but probably represented that we could go with adjacency list, or I don't know what else is more efficient. Represent this. So if I'm using adjacent, if I'm representing as an adjacency list, so that means so I need, so is that okay? There should be some label maybe. So maybe can I put some label like if this is 1, 2, 3, 4, 5, and then 6. So if I have 1, this is adjacency list, then 2, 3, then 2, 5, 6. If this is 3, this is 4, 6, and if this is 4, nothing. And this is 5, also nothing. 6, also nothing. So 5, 6, 1, 2, 3. Then so if this is the first, so it's a root to begin with. And you have 2 nodes, so we can divide the probability. Then this one get 1, the node number 2 gets 1/5, and then there's there's 2 neighbors. So we divide that 1/2 further into 2. You got the 2 neighbors. So 5 and 6 have 1/4. So 2, and then if we traverse the graph, then we traverse to 5. And then 5, since 5 have nothing, then we can update the node, and I think maybe there may be some satellite data for each of the vertices, like this 1, 2, 3, 4. So we can have maybe we can have like instead of 1 how do I represent this? We can have like maybe some like a tuple. Let me see. I don't know if that or actually. Or we could have it like separate, store as a separate array kind of. So depending on how many vertices we have, so we may have like probability array. So maybe this is like word and node to n vertices, so it should be 0 to n. So instead of so maybe instead of 1 to 1, maybe make it like all 0 0 base, but we can change that later. But anyway, or maybe we can skip the 0 index, so we can ignore and then start with 1. So each index in this probability array corresponds to the vertices. So we can update the probability into it as a separate array. So as we go down, so that means for vertex 1, we can update this probability array for at index 1 to be 0, and then when we go to 2, we can see 2 have children as our neighbors. Right? Then we can assign that probability for that vertex 2, which is at index 2, to be 0. And then when we go to 5, there is no more neighbors, so we can update whatever is getting calculated and passed on to So the node 5 and update the probability array at index 5 to be 1/4. So I think that is a strategy. It sounds good.
Sure, sounds good.
Yeah, and then also update. To update the probability array, probably we need to like do the addition. So initially, this will be initialized to 0 for sure. If it's initialized to 0, that means if any vertices have neighbors, we don't need to update anything because it's already 0. And then
Okay.
yeah.
Okay, so you're just adding the probabilities to the probability array.
Yeah.
How do you know to start from one? Are you always going to start from 1?
I was going to. I mean, depending on how many vertices, if there are, let's say there are n vertices, and then I can, and then I have the array, or I have the adjacency list. I can start with 0 base or 1. It doesn't matter.
Okay,
so
but
I can.
that's not what I'm saying here. How do you know that
Okay.
to start from here? What if you start from?
Oh, I see.
All right, if you start from here and then you say, oh, no children, 0, done.
Oh,
6 and 1.
Oh, I see what you mean.
If this was 6 and this was 1, and I start from 1, and then this goes, oh, no children. Okay, so this is 1. Everything else 0.
Okay, so this means so is it so the debt is being passed down? Is it? Are you saying that this can be? This is not a adjacency list, or is it like you can start with any node, any vertices? Is that represented?
Yes, so DAG is just this. It's the adjacency list. So how do we know to start at 1?
Okay, so this is okay. So sorry, let me see. So that is like any vertex you're talking about, right? You're saying?
No, DAG is the adjacency list.
Oh, it's adjacent city.
So DAG points to this whole thing.
Okay, I see. And then we don't know if this is the starting. We don't know if the first one is always here. You're saying it could be starting with this.
No, it's that we don't know which one it starts with, right? How do we know to start here, given this DAG?
Oh,
Let's say this was 6, and this
I
was
see.
1, and then we had this
Oh,
being
I see.
swapped so that it was like this.
Okay. Oh, I see what
Right.
you mean. Okay.
How do we
I
know
see.
to start from this one and not this one?
I see. Oh, that makes sense. Yeah. So definitely, I need some ways to by traversing the debt to find out. Well, if this is there's no neighbor, that means this is certainly not the not what I want to start with, because it could be at the leaf, right? So any any vertices that does not have any neighbor is not what I want to begin with, and that leaves with the vertices that have the neighbors, and uh, we want to find out if there's any uh, vertices that does not have any that does not have a parent. Um, so in this case, we can like find out, like for example 2. It has neighbor, but actually it has a parent. So it has a parent being point to. So in this case, we don't want to start with this guy. And same thing. Let's see.
Sorry, let me update this so that this is.
Oh, this is not. Yeah. Okay. Yeah, that's right.
Okay, so here we have. Okay, now
Yeah.
it's right.
Yeah. Yeah. So we don't want to start with 2 because there's another node. There's another vertices that has 2 as a label. And then 3, same thing. There's another vertices that has 3 as a neighbor. Then we don't care. We don't want to start with this because there's no neighbors. And then this one is 6. So then there's no one whose neighbor is 6. So in this case, we know that 6 is the one that we want to begin with, and then we can start with 6. But then in order to find out this, I think what we can do is when we traverse the deck, let's see, if there is if any vertices have a neighbors, we can keep track of that in a separate data structure, like maybe a hash set, or keep it as a set. So for example 2, put that in a set since they are neighbors. And then also 3, 3, 2, 3, and 6. But then in order to determine which one is the root or the starting vertices to begin with, we need to traverse its neighbors, and then for each neighbor we can query that set and see if there is a if we find that one. If we find that in the set, let's say 5, if there's not finding anything, I think we can just skip it. And same thing for 1, and then 3. We also need to find if 4 is in the set, which is no, and 1 is no. And then for anything that doesn't have a neighbor, we just skip it. We don't need to add that into the set. And then 6, we add it to the set, and then we need to like look at the neighbors and see if the set had any of this neighbor. In this case, actually there is 2 and 3 in the set that match 2 and 3. So we remove the ones in the set that match the neighbors. And then at the end, what is being left in the set would be the one to start with, which is 6. So we can use a separate data structure, and then by traversing that, and then iterate, and then also make sure to see if the neighbors are in the set, and if so, we move from the set, and eventually we will get there should be remain only one vertices.
It wouldn't be just 6 though, because you said we ignore 4 and 5, right? Is that what you said?
We don't need to track 4 and I don't think we need to track 4 and 5.
So if we ignore 4 and 5, then wouldn't 5 and 4 still be in the set?
No, it's just no. I'm saying that we don't add this. We don't add any vertices that has no neighbor into the set. So if we want to have 2, we add to the set, and then we look at its neighbor and see if any neighbors are in the set. If it is none, then we can continue, and then we add 3 into the set, and then traverse the neighbor, see if any neighbors are in the set. If there's no, we continue, and then 4.
Okay, so let's slow down for a bit here. At this point, put down a set. Okay. So at this point, is it empty or is it completely full?
At the beginning, it's empty.
Okay, it's empty. So you go to 1, no neighbors, so you don't add anything to the set.
I don't. Yeah, right.
Okay, 2, you have 5 and 1.
I add the 2 first.
So you add 2 to the set.
Right.
Okay, and then 3, there's 4.
I also, yeah, I also add 3, but yeah. So when I add 2, I also need to check if any 5 or 1 are in the set. Is no, then continue, right? So and I go to 3, I add the 3 also. I add the 3 here, and then also check if its neighbors are in the set, which is not in the set. So I continue. 4, there's no neighbor, I don't add it. 5, there's no neighbor, I don't add it. 6, there's neighbor, I add this. And then I check if the neighbor of 6 are in the set. In this case, that is, so I remove each one by one.
But you still go through in the order of the keys from 1 to 6. So then wouldn't that depend on what you see first?
It's
Let's say that 5 and 2 was swapped, right? So I have 5 here and then
okay.
2 there. So then 5
Okay.
would go to 2 and 1, and then 2 would have nothing.
Let's see. So 5, 2, 1, 6, 2, 6 is
Let's say
6
I
is
still have something
3,
here,
5.
right?
Okay.
2 goes to, let's say, like
Okay.
7.
Okay. 2,
And then
7.
here I have 7 with nothing, and then 2 that points to 7.
Okay. And then 6 will be 3, 5, right? 6,
6 would
3,
be 3,
5.
5, yes.
And then 3 should be 4, 1. And then 2, and then 7, nothing. And then 3 is 1, 4. Okay. So 2, 7. So 7, I don't add. 2, I add that, and 7 is not there. And 3, I add that. And then 1, 4 is not in the set. And then 4, there's no neighbor, though I don't add it. 5, 5, maybe I should just update here, sorry. 2, I add. 3, now I add 5. And then 2, 1, 2 is in this, that I remove it. 1 is not, and then I add 6. I add 6 here, and then I look at 3, 5. 3, 5 are in the set, so I remove them. And then 7 is no neighbor, so I don't add it. So end up at the end, 6 is the vertices I begin with.
Okay, then what if I had this? Oh, sorry. What if I had this? So, is this still
okay.
a DAG?
Oh,
So this would be 7 to 2.
7 to 2. So I will have 2. So I will have 2. So I will have 2 vertices yeah. So end result I will have 2 vertices then, right? That's the case. So this is still a valid DAG, right? So in this case, this will be 0. But how does the probability go? So this won't be 1/4, right? In this case, is it? This will be 1, right? There's only 1. So the probability when it goes down will be 1. So does that mean this will be adding 1? If this is the 3, then I think it is still then I think it will still be fine because I have 2 remaining vertices. Those are the only 2 vertices I will start starting from, right? So if I start with this one, so this is 1. So if I start with 7, so there's only one neighbor. So that means the probability is 1. And then so instead of 1/4, actually this will be 1, 2. So this one will have 1. And then because there's nothing. So this part I traverse this is done. And then the next one I need to traverse is starting from 6. So, and 6 will just go through the same thing, like I described it, and then it will also correctly update the probability if we traverse down from 6. So at the end, I think it will still be fine because I need to traverse starting from 6 and also 7 as well. So this will be the 2 starting vertices. I need to begin with. Does that make sense? Though?
So this value, 1 plus 1/4, will work. We want the distribution from the perspective of the whole graph.
Okay.
So how do we get the whole graph? If we have, let's say, 2 entry points, then immediately we already have 50% of our grasshoppers going here, 50% going here.
Oh.
Your probability needs to sum up to 1.
Oh, I see what you mean. Oh, okay. If that's this, okay, I see. So okay, then that may work too, right? Because I have so let's say I have 2 vertices. So that means I need to divide it into 2 I need to divide it evenly, right? Because those are 2 vertices in the deck that I can start from, right? So that means whatever there are how many left that I can start from. So it could be 6 or 7, or there may be another one, right? Whatever, right? 8 or whatever, right? 8 or whatever. So whatever, then I will capture that in my set, and then that means I will equally divide the distribution probability, and then for each one, then I will start. Let's say I start with 6, then I will have evenly divide the probability to begin with for each one. So 6, I pick 6 to begin with, or I pick 7. It doesn't matter. And then I should be able to update the probability to every neighbors.
Let me give you another problem here. So we have 1 that goes down to 2. 2 goes to 3, goes to 4. Then we have 1 that goes to 3. And then we have 1 that goes to 4.
Okay.
So if we do things like this, so in our DAG, with our adjacency map, we go from 1 to 2, 3, 4, or let's do 4, 3, 2. Right, so 1 points to 4, 1 to 3, 1 to 2, correct?
Yep.
2 to 3, 3 to 4.
2 to 3, 3 to 4, yep.
So in this case, we go from 1 to 4, so this would be 1/3, 1/3, 1/3, right?
Yeah.
Let's say I start and we do this whole thing, and we say that it starts at 1. So this is 1/3. Then this is 1/3. Then this is 1/3. Okay, we go down. 2. 2 has 1. What's the probability of this? 1/3. So we add 3 with 1/3. So this is now 1/3, 2/3. Now we go 3 to 4. What's 3? 2/3. What's 4? 1/3. Okay, so this would be 2/3 plus 1/3. So now this would be 1. So we have 1, 2/3, and 1/3. Does that sound right?
Let me see. Sorry, I'm drawing on my other piece of paper just to be very clear. So for 1, so 1 and 2. Yeah, 1 and 2, they should be, oh, sorry, no. So yeah, 1 is the beginning with, yeah. And then no, 2 should be, no, 2 should have 0, and 3 should be 0. 1, so 1, 2, and 3 should be 0, and then 4 is 1, right? Because 1, 2, and 3 has neighbors. 4 doesn't have, so we end up 4 is 1.
So could you repeat that one more time?
So 1, 2, and 3 will end up having probability 0 because they have neighbors. And 4 is the only one that does not have any neighbors. So that
Okay.
4 will have the probability of 1.
Okay. Let's say we did this out of order.
We did this out of order.
So we go 1 to 4, and then 3, and then 2. So we go 1 to 4. 4 has no neighbors. Okay, we exit. Now we go to, let's say 2, right? Well, this is already at 0 because we went down to 4. And then we have 2, and then 2 has 1 neighbor, so this goes to 0, and then it goes 1/3, so to this one. But since we already went to 1, this would now be 2/3, right?
I think so. We need to go. I think so. If we go out of order, like you asked before, and I don't think we can get the probability right? Because if you go out of order, you mentioned, let's say if I start with 3, then it will not be correct, the probability. So in this case, I need to find this guy to start with. Right. If you start with 2 or 3, it won't get the probability right for the whole graph, right? So we have to start with the right vertices. In this case, is 1. So that means the key is to find this to begin with.
So there's this thing called topological sort.
Right.
So topological sort is ordering of a direct graph in a linear way, such that all the directed edges in the ordering flow in the same direction. So either way, when we start with 4, it would not be okay, because after we update 4, we would be double dipping since we go from 4 back to 2. So what we need to do is make sure that 2 comes before 3 comes before 4. As we sum up the values. Okay, so here, this problem, we're at 620. I joined around 608, so we're already a bit over time. I want to spend some time talking about this problem here. Just like before, I'm going to write down the problems that we went over. So I'm scrolling up to the first problem. First problem is this. You can see in the LeetCode problem. Second problem looks like this. It also ties in with the first problem. So it's this. So that's the general gist of it. But for the acyclic graph, it's hard because you're transitioning from a tree to a graph, and you need to forget everything you did for the tree in order to do the graph problem correctly. So that's about it. In this case, what we're looking for here is for the first problem. I'll go problem by problem. So first problem over here, we're looking for can you do tree recursion? Which yes, you can. This one looks fine. I think this part we don't need, because, or this line we don't need, because this line already covers it. So that's just a small thing to worry about.
Makes sense.
And what we want to look for here is in the future, try to make your own node class. So do this yourself. And then what else here am I looking for? Time complexity is good. Space complexity is good. You notice that it's the maximum height of your tree. So that's good to note as well. Now let's go to the DAG part. So DAG here, using an adjacency map, mentioning the adjacency map is good, but you need to consider inputs or edge cases on your own. So stuff that involve like multiple nodes that have no incoming edges is something that you can take care of. Knowing that a tree is a DAG, but a DAG is not a tree, is also important. And then also going in order of the keys that you designate is skipping a step. So for this one, we need to look at, if you scroll down a little bit, looking at topological sort. And for that, we need Kahn's algorithm. And then, here's the LeetCode problem. You can also look up Kahn's algorithm in order to figure out how to do this problem more efficiently. That's about it. Another part to build upon this, for the third part, it would be something like, what would happen if we had a cyclical graph? or we weren't able
cycle.
to determine whether or not we had a DAG or not. So just a cyclical graph. If it's a DAG, we'll update it. If it's not a DAG, then we don't. What would we do? How would we do it? You need to be a little bit more familiar with how
Okay.
the DAG would work and what it would look like.
So this one you're saying if we find a cycle, then we just exit. That means we cannot fill the
That
public.
would be part of the interview. They would
I
just
see.
it's more or less you have to drive it in order to finish the problems, because
Okay.
the making the distinctions of what would happen if there was a cycle, what would happen if there was no cycle, that's something that you need to confirm, basically. Um, that's something that you can look at, but the main part of this is when you do the problems, look at more edge cases, and then also when you do the problems, you have to be a little bit faster. By the time we finished this one, I think we were at 30 minutes in, which is good. But for this one, the thought process took too long.
Yeah.
So just focus on getting the getting the problem done faster.
Yeah. You have the legal problem for the third question about the cyclical graph.
But the cyclical on leak code. Is it?
Oh, I don't know. Is that?
Are you thinking about this problem? This is a good problem to attempt after the interview. But then there's also a thing called Markov chain. Or Markov distribution that you can take a look at. After this interview. Okay. We're a little bit over time, but do you have any other questions for me?
Yeah. So the topological sort, is this a more more frequently asked? I guess graph in general.
It's commonly asked for many interviews, companies, not necessarily for Google. It is fair game though, so it's something that you should probably look at.
Okay, I see. So for this problem, this solution, you're saying that. So that means I have to use the topological sort approach rather than like figuring out what's the vertices to begin with.
Sorry, what was your question?
So, I mean, it says for this second part of the problem, yeah, saying that topological sort will be the solution.
Yeah, that would be a solution, yes.
Oh, okay. That would be maybe one solution, I guess. But what is but in case what is the problem like with my approach in this case?
What was your approach?
Yeah.
Can you explain what your approach is so I can tell you what's wrong with it?
Oh, right. Well, my approach is like we discussed. We need to find out the starting vertices. That may be one or two or three. So in this case, I think you bring up like there are two vertices. We should start the distribution. So, and I think my my approach using a separate set to figure out the number of vertices to begin with. I think that works. Like even for this problem, this is the problem I'm given to then that.
So what was the problem?
Oh, that
What was the thing you were wanting to mention?
I want to mention whether
set with multiple nodes. So first of all, set with multiple nodes right here with this solution, you have a probability that's greater than 1. It's not something that we're looking for here. So what we would have to do is generate all the paths, possible paths in our DEG. And the time complexity for having possible paths in our DEG is grows as the more it becomes more complex the more nodes that we have added. So this is only the case where we have 2. What if we had additional ones? What if we had some here, 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 and here, right? What if this one also had a value as well? How would we be able to consider the ordering in which we would traverse through the nodes in our graph? I can sit here and think of more examples in which case having to start with multiple values would not work, but I want you to investigate and try a solution, implement your solution, and think of ways for it to not work. Because I could sit here and explain it to you, but if you're still skeptical, then I can't do anything about it unless I do the problem in front of you right now, which will definitely take us too much time.
Yeah.
So
implement
the solution, and then once you find out why it doesn't work, then you'll understand it better than if I told you.
Right, I see. Yeah, that makes sense.
Okay.
Yeah, that's good to know.
Sounds like you also have are kind of confused about how you would implement it. So I would be also confused about telling you why it wouldn't work if that is also not clear yet.
Yeah.
And also, it'd be a better learning experience if you did the problem yourself. Do you have any other problems besides having me do the problem for you?
Yeah, I think that's fine. Yeah, I think I need to go back and just implement that. And I think that's good. Thank you for the time.